Good afternoon, everyone. Welcome to the midterm project report meeting for the project NCHRP-209. The title of this project is an automated system for pedestrian facility data collection from aerial images. The outline of this presentation is, in the beginning, we will just go over about the project, what is the goal, and what is our solution. And after that, we will discuss in detail about the 4 tasks we have conducted in the first stage. And as you can see, the task number starts from task 2. That's because, as required by the grant, our first task is to have a kickoff meeting with the expert panel, and that has been done already. So we won't be going through that task again here. And after the presentation of the 4 tasks, we're going to talk about the next stage, what we need to do, and then after that we can have a discussion. So as a reminder, this project is to develop a system which can automatically collect information about major pedestrian facilities from aerial images. And the 3 information or 3 data sets, 3 data we want to collect here in this project is marked crosswalk presence, marked crosswalk length, and paved sidewalk presence. And here is our solution in the picture. So we propose to develop a data collection system in this big box. As you can see, there are 4 components there, but the input of this system is gonna be the satellite image, which are already available in state DOTs. And our system can be fed by this aerial, or we call it satellite view image of your area, and then it can generate the output as a set of data. And here we just manually populated a table like that to show you what's the information we can collect. So for a given location X and Y, we can detect if there is a crosswalk or sidewalk presence. If yes, then there will be a Y. And if there is a crosswalk present, we will automatically measure the crosswalk length. So here, on the satellite image, we see, or the system sees there is a crosswalk, and then it automatically measures the size of it, which is 44 feet. That's how the system would work. And to realize this automation, there are 4 major components in this system. As you can see in this big box, we have model 1, that is the data acquisition model. And this model can prepare the training samples for the detection models automatically. And then after we prepared those training images, we can feed those images, or we call it training, the facility detection model. That's the second model. And this model will identify and classify objects detected from any satellite images. And then if we got a clear view of that target, then another model, mensuration model, will be developed to automatically measure the size, in our case the length, of the crosswalk. But if the view is occluded, like the sidewalk or crosswalk is heavily occluded by trees and shades or buildings or cars on the satellite image, and then in that case, we need to use another model, which is called occluded facility checking model, to check the street view of that same location for the same target. And in that way, we can have a double check to see if there is or not a crosswalk or sidewalk. And after the occlusion detection, we can again measure the present facility. So here are the four models included in this system. And the first stage of this project is just to develop each one of them. So first, we developed the data acquisition model. The purpose of this data acquisition model is to automatically prepare tagged images of crosswalks and the sidewalks to train, validate, and test the detection model. So because if you want to train a machine to automatically find the target and classify it, first you have to teach it. And the way you teach an image detection model is you have to feed them the images that already been tagged. So the machine will read or see a lot of images, like image tagged as crosswalk, and there is a crosswalk in that image, or image tagged as non-crosswalk, and in that image, of course, there's no crosswalk, it's just a pavement of road. And the same case for sidewalks. So we need to provide as many as possible such tagged images to train the model, and to prepare those high quality tagged images. Traditionally, we can do it manually, like we hire students and let them check each image, and then if there is a crosswalk or sidewalk, they can give it a label as crosswalk or sidewalk or none. That's the traditional way. But the traditional way has some limitations. The first thing is it doesn't cover, since this project is only 2 years, preparing such amount of data would require a lot of time if we do it manually. And a second thing is if you hire people to collect the data in a limited amount of time, and then they tend to observe on Google Street Map or Google Satellite Map or Bing Maps. They tend to observe those locations where our views are clear, or where the target is easy to be detected, or it depends on how you train these students. They tend to select the image or the targets which is easier for them to detect. Like if they're not familiar with different patterns of crosswalks, they might just select the zebra crosswalk because that's the one they are familiar with. So you won't be able to have a very diverse set of images where it covers all different types of crosswalks and sidewalks in the real world. So that's the two limitations for manual data collection. But of course, if you have a long time to focus on this image data collection, and then you can figure out like how to train your collector and how do you guarantee the diversity of those images. And there are some pros for the manual data collection, of course, but because our limited amount of time here, we try to do it automatically. And the final results of this data acquisition model is gonna be we have a set of positive samples. Positive samples means all the images in that data set is of sidewalk or crosswalk. And the other negative samples are those images of where you don't have any crosswalk or sidewalk at all. So to get this data, automatically we have to use two data sources. The first one is the OpenStreetMap. So OpenStreetMap is an open source mapping tool. So everybody can contribute whenever you see something, you have information about a location. You can literally open their map and use their editing tool to point that location and then give it some description and labels as required by the OpenStreetMap manual. So there are some specific taggings and specific methods you need to follow to edit or add any information in the map. But thanks to this OpenStreetMaps, there are some pedestrian facilities tagged there. For example, if you tag highway equals to crossing, that means there is a crosswalk on the map at the location where you point the dot. And another example will be if the sidewalk equals to both left, right, and no. That means there are sidewalks either on both sides of the road or on one side, or there's no sidewalk at all. So by using these tags, we can easily get the locations where there is a crosswalk or not, or a sidewalk. And another data source is the Bing Maps. We didn't use Google Maps because there is some limitation on how many times you can query for their images, and but for Bing Maps there is not that limit at present. But we're not sure if in the near future both companies will realize such research activities, and it depends on how they are open to the research, to the researchers and educational side of this mapping things. So, but right now we just use the Bing Maps, and it provides good quality satellite images and street view images, as good as Google Maps, and so the Bing Maps is used for us to extract the satellite image of that location we just identified in OpenStreetMaps. So, and here is the method we use to automate this data collection work. So as you can see, it's starting from the taggings, right? On the left side of this image, we have all the taggings. And the first box is to query for the negative sidewalk locations. Negative sidewalk locations means there is no sidewalk at all on either side of the road. So the tags we used here is sidewalk equals to none or sidewalk equals to no. There are two tags in OpenStreetMaps, but they are the same. They all tell you that there is no crosswalk at all. So if we have codes to query for sidewalks equals to none or no in the OpenStreetMaps. If we do that, and we have done that, okay, so if it's done, and then the OpenStreetMaps will return you a location, a set of locations where the tags are sidewalks equals to none or no. So we will have a bunch of X and Y locations in degree from OpenStreetMaps. So this this image is a screenshot of those locations, like location ID 3334. We know the lat and the long of that location. And since we query for sidewalks equals to none, so we know this location is where there's no sidewalk at all. And after that, we use that location or the set of locations to query for the satellite images from Bing Maps for those locations from Bing Map. So this is gonna be one case. If we use the ID 3334's location lat and long, and then we query for the satellite image for a fixed size and a fixed resolution, then there will be a satellite image for that location, and here is that image, and the size and the resolution, those data or those specs are determined by our researchers through trying different sizes and resolutions and find the optimized look. So I think that's also one of the contribution we did, because looking at different targets, you need to have different resolution and the size of that image. So pretty much you can cover or the image can include the most part of that target, and you still can have a decent look of like the pattern or the boundary. And that specs, like the resolution and the size, is gonna be different for different targets, different facilities. So again, in this project, it's not just to use the machine learning cool methods to apply in the transportation field. There are a lot of specs and challenges you need to figure out in our field to make this tool customized for our targets. So this is just one of the examples, and we'll talk about more challenges in our project, of course. All right, so let's go back to this image. So once you have this satellite image extracted, and then you can store that image in a directories. So we have different data sets where you have those images, and you have the label, and you have the information of the tags. So that's gonna be our one set of data. So this is gonna be our negative sidewalk data set. All right, and then let's go back to the left side again. So the first tagging, we can do the negative sidewalk. So we can generate a data set about negative sidewalks. And then we can also use the same pipeline to extract the satellite image for positive sidewalk. The way we do that is we just use different tags. So the tags we're using is sidewalk equals to left or right or both. So those will give you a set of locations, of course, and then we use those locations for Bing Map and get the positive sidewalk images. And this is one of the images we collected. So you can see on the two sides of the roads, there are sidewalks. And when we collect all the data, here we have a data set of positive sidewalk. And let's go back to the left side again. The third tagging or the third data set we want to collect is the positive crosswalk. To do that, we use the tag highway equals to crossing. So that's where you have a crosswalk tagged by the map users. And then we query that tagging in OpenStreetMaps, and then that OpenStreetMap will give us a set of locations again. And then we use those locations to query for the satellite image from Bing Map, and then we can have a image of a crosswalk. And here is an example. And after that, we can have a set of data tagged as crosswalks. But here we are missing the negative crosswalks. So negative crosswalk is a little bit challenging because of course you can have a tag as highway equals no crossing. Yes, we can do that. There is a tag, but if we do this tag, if we query for this tags, the location we get And the satellite image we get is very confusing because that location is gonna be very close to another leg of that intersection. Because if you have a location supposed to be able to cross, but there is a fence or there is a barrier that you are not legally can cross, that locations will be tagged as no crossing. But think about that. Those locations is gonna be where? It's gonna be near the intersection, on the leg of intersection. So if we query for those locations and we extract the image, and that image is gonna include the other legs, the next leg, and on that leg there might be a crosswalk. But without manual checking, we couldn't know. So in that case, if we use this tagging, highway equals to no crossing, we are going to have a bunch of images where it tagged as no crosswalk, but in the image somehow there is a crosswalk in the image. So, and that's confusing for the training, for the model itself. And we don't want that happen, so we need to find out another way to get pure to get images that there is no crosswalk at all. So that's one challenge. And the way we do that is so this is a different method than than this one. And this method is just for the negative crosswalk acquisition. And the way we do that is first, so in an area, we can randomly determine two corners of an area in a city, and then in that area, we want to find the positive crosswalk locations. That's the blue dots in this map. So we do that in the OpenStreetMap again. We ask OpenStreetMap, where are the locations of the crosswalks? And then it will give us a set of locations X and Y. So that's all the blue dots. And then we move on to the Bing maps. We can generate a route passing through those blue dots. That's a function in Bing Maps. That's where you can use the routing function. So you have a route. That's the dashed red line passing through all the blue dots. And then after that, we move on to the step 4, which is to randomly drop the yellow dots on the routes. And so you can see some of the yellow dots are gonna be in between the adjacent two blue dots, like this one. So that yellow dot is in between the two crosswalks because blue dots are crosswalks. So we assume that the roadways or the pavement in between two adjacent crosswalks are gonna be pure pavement. So no crosswalk in between two adjacent crosswalks. That's an assumption. So we can use the image of those yellow dots as no crosswalk images. And one challenge here is we drop those yellow dots on the route randomly. So there are gonna be yellow dots very close to the blue dots. And so we have to filter out those close pairs, like if a yellow dot is right on the blue dot or in a range in a buffer zone of that blue dot, we have to filter out those yellow dots so that all the yellow dots and images of that yellow dot we have is just the pavement without a crosswalk. So that's the way we do the negative crosswalk acquisition. And the results are really good. You can see those examples, they are not crosswalk at all. They're just in the middle of the highway or on the road or on a street. So no crosswalk at all. And here is how do we filter out those duplicates. So one thing is, of course, you have yellow dots too close to the blue one, so the image will look pretty much the same. And we have a set of codes can help us remove those duplicates. And here is one example. You can see these two images are pretty much the same, just a little bit different. And so we want to remove these duplicates. And another thing is, it's not just because the yellow dots can be closer to the blue dots. It's also because in a machine learning training, you don't want to use the duplicated images, both in training and in testing. Of course, in training, it's fine because you're just looking at, or the system is just looking at a similar target several times. It's okay for training, for learning the features. But if you happen to have one image in training and you have a similar image in the testing, then the testing results or the accuracy is gonna be boosted up, but that high accuracy is fake. There is a cheating thing there. Just like you have the students look at the same question in the class and then let them to do it in the final exam. That high score is not true. So that's why we also want to remove the duplicates anyway in the data set. And to prepare this large data set, another way, it's a very standard way in machine learning, is to augment some images. The augmentation either will change the tone of that image. So like this first case, we have a lighter tone and we have a darker tone. So it's just to look at something in the same location but in different light conditions. And then another way to augment the image is to rotate that image in different angles. It's for a machine, it's like to look at the same target in different angles from different perspectives. And all of these are good for learning, but we don't want to have those images in learning and at the same time in testing. So after all this data collection, duplicates, removing, augmentation, and then we have 4 sets of data, tagged images. The first set is the negative crosswalk data set. We have 2,284 images. And second data set, we have the positive crosswalk data set, 2,096 images tagged as crosswalk. And then we have negative sidewalk images, 8,417. And then we have the positive sidewalk data set. It's 21,033 images. So that's the raw data set we collected in the first task. And then here I will pass this presentation to Bailey. He is a PhD student and he's the main researcher in our project, and he will introduce you the facility detection model and the occlusion detection model and the mensuration model.